Hello, this is video 12, and as you well know, we have been looking at number systems pretty in depth. What we haven't looked at that we need to look at are conversions between all these number systems, all the strange and wonderful combinations we can get of those number system conversions. Is that the best way to say that? I don't know. Conversions between number systems. And let's see, how many possibilities are there? There are binary to decimal, base 2 to base 10, and back, decimal to binary. Three, we've got the hexadecimal, binary to hex, our insider abbreviation for hexadecimal. 4, hex to binary. Wow, there's a bunch of them. 5, decimal to hex. And 6, hex to decimal. All possible back and forths. Start with the number in one number system, go to the number in the other number system. Oh dear, this is going to take us all weekend. Although, hold up a second. Binary to decimal, that's when you have a bunch of zeros and ones and you want to find out what that really is in base 10. Deja vu all over again. We've done that. That's when you throw all the zeros and ones on a place value chart, multiply each of the ones times its place value, and you can multiply 0 times this place value if you want, but it doesn't contribute anything. So we already know how to do that. All we got to do is draw our little handy dandy place value chart for binary and add up where all the ones are. Done and done. Decimal to binary, yeah, I think that's still on the to-do list. Binary to hex, you know what? That rings a bell as well. Binary, the long string of zeros and ones, and I remember, let's see, is it start on the left, start on the right, start on the right as well? Yeah, start on the right to make sure that you have nothing but chunks of zeros and ones, 4 of them in a row for each hex digit. So you start this one. You start with a bunch of zeros and ones, start on the right, start marking off groups of 4, and if you run out before the last group of 4, you can always put zeros on the left-hand side and everything's still fine. Check. Done and done. Hex to binary. That's where we take each hexadecimal digit, those weird ones, the A's and the B's and the F's and all that stuff, including those 0 through 9. And let's see, what do? You have miniature little explosions where each one of those bursts into a chunk of 4 bits. So for each hex digit, you end up with 4 bits. And check, please. Get rid of that. We've already done that. We already know how to do that. A lot of this was covered in previous videos. Decimal to hex, I don't think so. Hex to decimal, that was the weirdest one you remember, with the ginormous labels on the place value charts with non-trivial multiplication that even had to be done outside the video so your humble instructor could use the calculator. So it looks like we're almost done. We've already got, 1, 2, 3, 4 out of 6 of these. That's done. These are done. That's done. No, I erased the wrong one. That one wasn't done. Silly me. Oh well. What's left? It was what? Decimal to binary. That one was not done. And the other one, it was the decimal. Decimal is the outlier. All of a sudden, decimal is the strange one in the list, where binary and hexadecimal fit together and play well together and everything. They love each other. But decimal and binary, they don't really get along as well. And decimal to hex, I'm putting off the worst till last, I guess. Decimal to binary, what, for example, if I start with 200, which cannot possibly be a binary number anyway, but for emphasis, I'll put a little 10 down there and say, yeah, you know what? That's in base 10. Base 10. Here comes the handy dandy place value chart I got to convert it to binary, so this will need to be a binary place value chart. And I'm not sure how many columns I'll need. If I need more, I'll put some more. But here we go. Ones place, and remember, every time you move a notch to the left, you double it. 1, 2, 4, 8, 16, 32, 64, 128, and that might not be enough. How do I know? Because 200 is more than 128. What's the next one? I barely have room. 128, then 256. That's more than enough. That's too much. That's a Price is Right game. I just won a car. 256 is too much. How do I know? Well, I'm not going to have any ones over here. Think of this as 200 marbles. And I'm trying to keep up with how many marbles I've got by putting a tally mark in each one of these counts on the way down. I am not going to be able to get 256 marbles out of my drawer if I've only got 200 marbles total in my drawer. So I am not going to have a 1 here. I'm certainly not going to have a 1 any further across. There are not any chunks of 512 I can pull out of 200, and so on. So I don't need any of the place values off to the left of that. The first one I might possibly need, let's see. Since 256 is too large, I look at the next one down. Can I get a group of 128 marbles out of 200 marbles? And the answer is yes. Yes, I can. And I'm going to take that chunk of 128 out of my 200. Now, just pause a little bit of a tangent here, and then I'll be back on track. Why don't I start at this side? Well, I can't look at that and know whether in advance, I don't know if this is going to need a 1 in the ones column or not, or in the twos column or not. I've got to work my way down. I take the biggest chunk of the 200 that I can out at one time, and then as I move across from left to right, try to figure out how many more tally marks I need, how many more chunks I can take out. Now I'm back on track, and you can watch and see what I'm talking about. Here's scratch work, S-C-R-A-T-C-H. Scratch this. 200 minus, I've already represented right here, that little one, dinky little one right there, by virtue of its place value, represents an entire 128 of the total of 200. 128. Rut-row, gonna have to do some math. Let me see, when I borrow, that's gonna be a 10. 10 minus 8 is 2. That leaves that at 9. I'm doing all this mentally. 9 minus 2 is 7. I think that's 72. Let me double check. 8, 9, 10, 2. 9 minus 2 is 7. Yeah. If that's wrong, I did it on purpose, see if you're paying attention. So that's 72. What does that represent even? If I've taken a group of 128 marbles out of my drawer that has 200 in it, that means there are 72 marbles left in the drawer. And I'm keeping a tally as I pull out groups of marbles. Can I get a group of 64 marbles out of the 72 that are left? In fact, I can. So that's going to need to be a 1 as well. 1 times 64, 64. How many marbles are still in the drawer? How many have yet to be represented? Well, I got to subtract again, got to borrow again. I could have come up with an easier math problem, couldn't I have? But I borrow, that makes that a 12, that'll be 8. 8, well, yeah, I think that's it. Right. So there are 8 marbles left in the drawer because I took out a group of 128, took out a group of just plain old 64. Now I look to see if I can get a group of 32 marbles out of what's left in the drawer, and the answer is no. There are only 8 marbles left in the drawer. Sorry, 32. No soap for you. 0 for 32. Let's try the next one. 16. Can I get a group of 16 out of the 8 marbles left? I cannot. 0. 8. Can I get a group of 8 out of 8? In fact, I can. If I take that group of 8 out, then how many are left in the drawer? 0. But I can't stop there. To get these in the proper place values in the place value chart, I do need zeros over here. I cannot get a group of 4 out of that. I cannot get a group of 2 what's left. I cannot get a group of 1. Put the little 2 to show that's a binary number now. And voila, as if by magic, we've got a representation of 200 from base 10 in our binary number system. How can we double check? I can't do this in my head, but I'll pretend that I can. If I multiply 1 times 128, add 1 times 64, add 1 times 8, that better add up to 200. Can I do that in my head at all? Well, we'll pretend that I can. Yeah, I just did that in my head, and that's 200. Is that good enough? Okie doke. Well, that's so much fun. Let's do another one. Oh, by the way, if all that made perfectly good sense, you can do that with any number. It doesn't have to be 200. You just make sure your place value chart is wide enough that you've overshot it a little bit. Right, label the columns until you've got the first thing that's larger than the number you start with. So if I wanted to represent 50, for example, I could have stopped right here at 64. Say there's not going to be any chunks of 64 out of there, or a chunk of 128 or anything larger. The first chunk would be a chunk of 32 to take out of the 50. See how to play that game? We'll say that that's also a check mark, and that we had to know, yeah, that too. We know how to convert decimal to binary now. What do we not know? Well, because it's in my nature, save the worst till last. Yeah, I admit it. I'm a procrastinator. We'll put off the worst one of them till the very end, decimal to hex. And I didn't mean to sour you on it before we even look at it. I didn't mean that. I mean that decimal to hexadecimal, that is fun. I've been looking forward to this all day. It involves long division. What could be more fun? Okay, enough of that. We need a place value chart. Let's say we're going to do 200 again. Okay, here's the hexadecimal chart. Big wide columns for a big wide number system. What do we need? We need a 1, 16. Wow, these get big in a hurry. 256. Well, you know what? The good news is that's all we need. Why? Because 256, we can't even get a chunk of 256 out of 200. So that's too big. We're not going to get anything in that column. That's going to be a 0, and so are all these other columns. If we filled those in, it's just going to be padding fluff, just a bunch of zeros, a bunch of marshmallow zeros that don't add anything to the magnitude of the number. Now, all we got to do is figure out what to put in the 16 column for crying out loud. Here comes the long division. How many? Here's the question we have to answer. How many groups of 16 can we get out of 200? Oh, here it is, scratch work, S-C-R-A-T-C-H. I'll start with 200, divide by 16. 16 won't go into 2, I can do that, yeah, it won't go. 16 goes into 20, one time, if you know how to do long division by hand. 1 times 16 is 16, write a 16 down there. Subtract, 16 from 20 is 4, 40. How many 16s are there in 40? Well, let me think. There is at least 1. 16 goes into 40. What about 2? 2 times 16 is 32. I can get 2 of them out of there. 3. What about 3? 3 times 6 is 18. 148. No, that's too much. 3 times 16 is too much. I can't do that, so 2 will do it. 2 times 16 is 32 with 8 left over. What does all that mean? Is that of any use to us at all? Well, let's see here. I have represented nothing. I've got a 12. Somehow or another I got to squeeze the 12 into the 16s column. Fortunately, in hexadecimal, we can represent anything up to 15 with a single digit. What about C? Will that do it? Isn't C the 12? Look it up and see what I did there. So we have what? We have everything except 8 represented. Well, just pop the 8 over here. C8. That C stands for 12. Let's do the math backwards now. And this is base 16. Base 16 says C8 should be equal to 200. How do we double check? C is 12. 12 times 16, if I do the math, it better come out to be almost 200, 8 less than 200. I multiply 12 times 16, add 8 times 1, that should add up to 200. Okay? Now, if I really want to be super extra careful, I might even switch colors. And check this against the other number system. Just turn this every which way but loose. C, the single digit C, if we decide to explode that into binary, is 12, which is 1 in 8's place, 1 in 4's place, 0 in the last two, 2's place and 1's place. 8 is a 1 in 8's place. I'm talking place value chart for binary right now. It looks like that. Does that bear any resemblance to what we just got for 200 in binary, base 2? Double, triple check our work. If all of those seem to match, then we're in business. Now, we don't have to do this, but that's kind of a parity check. In other words, it's an alternative way to check and see whether or not the answer is actually right. How are we doing on this? Does that make sense? The good news is I'm not going to ask you to do ginormous operations by hand using the hexadecimal number system unless it's the the hexadecimal to binary and back. Those are trivial. Anybody could do those. It's just marking off chunks of 4 and all that stuff. This is the weird one. This is the outlier. This is the painful one with by hand long division. But still, I'm going to put a check mark and say we know how to do it. We divide longhand division. We divide the largest, the largest place value that's less than the number. The largest place value that's actually less than the number in this case is 16. And I'm confusing myself now, so I think I'll stop while I'm ahead and hope that those two examples make sense. If they don't, come by during office hours, bring it up during class, or just stress out about it. Your choice. I'll see you online.